Fantastic news for the astronomy community. The Vera C. Rubin Observatory, located in Chile, just recently finished construction, and the first images were released on June 23rd. This telescope has been over 10 years in the making and will primarily survey the southern hemisphere over the next 10 years, primarily for creating a time lapse record, as well as studying dark energy and dark matter by observing various light sources in the cosmos. This comes from NPR.org. This observatory's first images are stunning, and it's just the start. Here's one image, absolutely breathtaking. Looks amazing. Millions of stars in this image, which this image combines 678 separate images taken by NSF DOE Vera C. Rubin Observatory in just over 7 hours of observing time. Combining many images in this way clearly reveals otherwise faint or invisible details, such as the clouds of gas and dust that comprise the Trifid Nebula and the Lagoon Nebula, which are several thousand light years away from Earth. Absolutely unprecedented detail. That is amazing. Amazing. So, a powerful new observatory has unveiled its first images to the public, showing off what it can do as it gets ready to start its main mission, which is making a vivid time lapse video of the night sky that will let astronomers study all the cosmic events that occur over the next 10 years. As the saying goes, a picture is worth 1,000 words, but a snapshot doesn't tell the whole story, and what astronomy has given us mostly so far are just snapshots. That was said by Yusra Al Saeed, a Princeton University researcher who oversees image processing for the Vera C. Rubin Observatory. The sky and the world aren't static, she points out. There's asteroids zipping by, supernovae exploding, which, by the way, a supernovae on average, like one per 100 years on average will explode in any given galaxy on average. And there's hundreds of billions of galaxies out there, so technically we would be able to observe dozens of supernovas happening on a daily basis, really. So anyway, and the Vera C. Rubin Observatory, conceived nearly 30 years ago, is designed to capture all of it. Quote, these images are fantastic. They're incredibly high resolution, but they're just a tiny, tiny fraction of what's been captured, says Kevin Riel, a staff scientist with SLAC National Accelerator Lab who is working at the observatory in Chile. He notes that the newly released image that shows many galaxies is a small section of the observatory's total view of the Virgo cluster. We just happened to zoom in on this little piece. I think they left an A out of there, but okay. Built with funding from the National Science Foundation and the Department of Energy, the facility will collect a mind-boggling amount of data on the entire southern night sky during a decade-long survey slated to start later this year. Here's another image of what appears to be thousands of galaxies that was also taken by the Vera C. Rubin Observatory. Absolutely amazing. Looks like galaxies merging here. From my observation, it appears to be 1, 2, 3, 4 galaxies that are pulling on each other gravitationally. I mean, these, what looks like clouds, are actually billions of stars that are being ripped out of these galaxies due to their collision with each other. At least that's just my observation. But anyway, so this image shows another small section, all these galaxies, thousands of them, but it's only a small section of NSF-DOE Vera C. Rubin Observatory's total view of the Virgo cluster. Visible are two prominent spiral galaxies to the lower right, three merging galaxies, the upper right. I mean, I think I see four, but all right. 1, 2, 3, 4, but okay. Anyway, I'll believe him. And also several groups of distant galaxies, many stars in the Milky Way galaxy, and more. I mean, to me, it looks like there's only about 20 stars in this image. I mean, just based off of like the Hubble Ultra Deep Field image, for example. I mean, you can easily tell which are stars and which are galaxies, at least with the Hubble observations, such as this one being a star, this one. I mean, if it looks like there's these cross-shaped rays that are protruding from the light source, that's usually a star. I mean, I would assume that to be one, as well as this one, this one, this one, this one, and so on. Maybe that one. Maybe not that one. Definitely that one. Definitely this one, and so on and so forth. I mean, I don't know. To me, I count like roughly 20, but Maybe I'm missing something. Perhaps some of these more faint white dots could potentially be stars too, but the vast majority of the objects in this image are individual galaxies, each one containing hundreds of billions of stars in each one of these dots, except for the 20 couple dozen stars that are in this image. So, this survey will compile observations on about 40 billion stars and galaxies and other celestial objects. Each one will be checked out hundreds of times, giving astronomers access to about 60 petabytes of raw data. Petabytes. So, how much is that? How much is a petabyte? So, 1 petabyte is equivalent to 1,000 terabytes. So, if you go on Amazon and you're looking for a portable hard drive that you're going to buy, chances are it's going to be anywhere from probably 1 to 4 terabytes. You can buy them up to 24. Actually, you could buy them up to 100 terabytes, really. They get obviously more expensive the higher you go, but for like $100, you can get a 4 terabyte portable hard drive, which will store pretty much anything that you're ever going to need storage with. But yeah, so we're talking 1,000 terabytes, just equivalent to one single petabyte. And again, they are talking 60 petabytes. So 60,000 terabytes of raw data. That's a lot, which the Rubin Observatory says is more data than everything that's ever been written in any language in human history. I mean, like, I get the analogy, but more data than everything that's been written. I mean, even if you're taking a photograph of every page of everything that's ever been written, I would assume 60 petabytes is way, probably hundreds and hundreds of times more memory than even that. Now, if you're talking just text, I mean, millions of times more data in 60 petabytes than all of the text that's ever been written in human history. Just in my opinion, that's just my observation. I mean, if you get out a keyboard and you type every single word of everything that's ever been written in human history, it's not going to come close to 60 petabytes or 60,000 terabytes of information. Quote, since we take images of the night sky so quickly and so often, we'll detect millions of changing objects literally every night, says Aaron Rubin of Stanford's SLAC National Accelerator Laboratory, who is part of the observatory's leadership team. He calls the Rubin Observatory a discovery machine that will enable astronomers to explore galaxies, stars in the Milky Way, objects in the solar system, and all in a truly new way. Already, in just over 10 hours of test observations, the observatory has discovered 2,104 never before seen asteroids, including 7 near Earth asteroids, none of which pose any danger. And there's an image of the observatory on the peak of the mountain. I'm assuming that is probably the Atacama Desert in Chile. Let's see. Oh, it's on Cerro Pachon in Chile during sunset. Mining the data. Named after an astronomer famous for her research related to dark matter, the Vera C. Rubin Observatory is perched on a mountaintop in Chile. It's equipped with a specially designed large telescope as well as a car-sized digital camera that's the biggest such camera in the world. The camera is controlled by an automated system that moves and points the telescope, snapping pictures again and again to cover the entire sky every few days. Each image is so detailed, displaying it would take 400 ultra high definition television screens. By constantly comparing new images to ones taken before, the facility's computer systems will be able to spot anything in the sky that changes or goes, or moves or goes boom, such as a supernova. It will be able it will be capable of really detecting things that actually change very rapidly, says Sandrine Thomas, Deputy Director of Rubin Observatory and the observatory's telescope and site project scientist. That in itself will be unique to the world. No other telescope would be able to do that. It has such a wide field of view and such a rapid cadence that we do have that movie-like aspect to the night sky. The observatory is expected to detect about 10 million changes every night and will send out alerts to consortiums of researchers, or consortiums of researchers, my bad. They'll analyze all that data and zero in on the most interesting changes to target for follow up observations. This should let astronomers catch transient phenomenon that they otherwise wouldn't know to look for, such as exploding stars, asteroids, interstellar objects whizzing in from other solar systems, and maybe even the movement of a giant planet that some believe is lurking out in our own solar system beyond Pluto, which is otherwise known as Planet X or Nibiru or, whatever name you want to give to it. Quote, it's a very special telescope, end quote, says Scott Shepard, an astronomer with Carnegie Science. It's going to find everything that goes bump in the night to some degree. It's going to be revolutionary, he says. Astronomers are going to change from observing little areas of the sky to basically data mining. It's going to be like a fire hose of data coming in. There's going to be all kinds of stuff in there, and we're going to have to sift through it to find everything. And I believe that's it. So, I mean, they might actually, I mean, they're going to release the majority of the data, the images, the information that this telescope captures. It's going to be released in the public in some way, shape, or form. And man, I think it was called galaxyzoo.org. Do I have that right? I think it was called galaxyzoo.org. I'm going back like well over 10 years. So, Zooniverse, maybe that's what it is now. You have witnessed what you're about to see. So, Galaxy Zoo, this was part of the Cosmo Webb survey, which, well, I mean, now they're using James Webb's telescope, but what it does is that it takes millions and millions and millions of images of galaxies, which, of course, that one galaxy that or that one image that I showed you had all these galaxies in it. So, what Galaxy Zoo does is that it actually takes individual galaxies from an image like this, and it creates a huge catalog of these galaxies, and it offers the public who's interested in astronomy to use their website to look at these galaxies and determine whether or not if it's an elliptical galaxy or a spiral galaxy, or it might ask other questions. Does this appear to be a galaxy merger, for instance? And you can check yes or no, or you can give your opinion on it, and they will add your answers into this broad catalog or categorization of millions of different galaxies that they've taken pictures of. By allowing the public to get involved, it takes away a lot of manpower from individual scientists, and it allows volunteers out in the public to help with this enormous catalog of galaxies that we've created over the years. So, yeah, Galaxy Zoo. I haven't even been to this website in at least a decade. I used to get on here a lot. It was pretty fun. 130,000 volunteers, over almost a 500,000 classifications, different subjects and completed subjects. So yeah, if you're interested in volunteering some of your time to the astronomy community, and if you only want to sit in the comfort of your own home on a computer and help out, this is one way to do so, which I'm sure there's many different programs. But anyway, so yeah, this was the end of the article from npr.org. I'll link it in the description, but also I've got some information here from Wikipedia, of course. So the Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, or the LSST, is an astronomical observatory in Chile. Its main task is an astronomical survey of the entire available southern sky every few nights, creating a time-lapse record over 10 years. The Legacy Survey of Space and Time, also abbreviated LSST. So let me try to make this a little bit bigger. Yeah, I think this could be read. All right. I always try to make sure the text is large enough for folks watching to be able to actually read it as I go along. So the Vera C. Rubin Observatory is a joint initiative of the U.S. National Science Foundation, or NSF, and the U.S. Department of Energy's Office of Science, and is operated jointly by NSF, NOIR Lab, and SLAC, National Accelerator Laboratory. And there's tons of information. I just highlighted what I just felt to be the most pertinent for this video. And it was first proposed in 2001 as the LSST, and construction of the mirror began in 2007. The LSST then became the top-ranked large ground-based project in the 2010 Astrophysics Decadal Survey, and the project officially began construction on August 1st of 2014. The U.S. National Science Foundation authorized back in 2014 $27 million of its construction budget, even though it cost a lot more than that. The total construction cost was expected to be about $680 million, the large majority of which was contributed by the U.S. government. Site construction began April 14th of 2015 with the ceremonial laying of the first stone. The first on-sky observations with the engineering camera occurred on October 24th of 2024, so pretty recently, while system first light images were released on June 23rd of 2025. which was only, what, 4 days ago as of my recording. Yeah, it's currently Friday, June 27th, and it's almost 2 o'clock p.m. my time, Eastern time. So anyway, full sky operations are planned to begin later in 2025 due to COVID-related schedule delays. Data is scheduled to become fully public after 2 years. So yeah, I should have highlighted that, but I read it, so there you go. Um, Quite a while. That's kind of a disappointment to hear that for the data to become public after 2 years, but I'll get to the reason for that. There is a reason for that, and it involves classified information, believe it or not. But anyway, I'll get to that. So the observatory named after Vera C. Rubin. Vera Florence Cooper Rubin was an American astronomer who pioneered work on galaxy rotation rates. She uncovered the discrepancy between predicted and observed angular motion of galaxies by studying galactic rotation curves. Her work on the galaxy rotation problem, and so on and so forth. There's a link to it if you want to check out Wikipedia. I'll put this in the description too, this link. And it goes over the history of the observatory and sky surveys and things of that nature. So in May of 2018, the United States Congress surprisingly appropriated much more funding than the telescope had asked for. Now, why is that? In hopes of speeding construction and operation. Yeah, but really, why? Telescope management was thankful, but unsure this would help, since at the late stage of construction, they were not cash limited. So I will get further into why that is. There is a reason for it, though, you know. So anyway, the Simone survey telescope design is unique among large telescopes. An 8-meter class primary mirrors and having a very wide field of view, 3.5 degrees in diameter or 9.6 square degrees. For comparison, both the sun and the moon, as seen from Earth, are 0.5 degrees across, or 0.2 square degrees. So it's got a very wide field of view. Combined with its large aperture and thus light collecting ability, this will give it a spectacularly large ITNDU of 319 meters square degrees squared. This is more than 3 times the ITNDU of the largest view existing telescopes, which is the Subaru telescope with its hyper suprime camera and pan stars, and more than an order of magnitude better than most large telescopes. There's actually an image down here somewhere. Let me see if I can find it without, completely losing my. Here it is. So this is a good indication as to the wide field of view that this telescope has. So that's the size of the moon. So you're looking up at the sky. Let's say this telescope is pointing up at the sky and it's got the moon in its field of view. Now you can kind of see how huge of a spot in the night sky that this telescope can cover. It's a very large area. And I don't know if it can, but I'm assuming it could probably even zoom in further than that. But I mean, I'm not 100% there. But anyway, so I'll move on here. This is under the optics section of the Wikipedia article. The telescope's primary mirror, or known as M1, is 8.4 meters in diameter, which is 28 feet across. I mean, I think that's larger than my living room and kitchen combined. It's a very large, very, very large mirror. Not the largest one out there, but it's a pretty good size, though. The secondary mirror is 3.4 meters or 11.2 feet in diameter, which they're showing the diagram of that here. So the M1 is this like plate here, or it's the mirror. That's the first one. And then you can see how the light will shine up to the secondary mirror, which is right here, which is the M2, which they said is 11.2 feet in diameter. Then it shines down to the M3 mirror. Oh, didn't mean to do that. Let's go back. So the M3 mirror, which is inside the ring-like primary, it's 5 meters or 16 feet in diameter. So this one here, 16 feet. And the secondary mirror is expected to be the largest convex mirror in any operating telescope. It doesn't exactly tell us. I mean, I'm assuming. Okay, hold on. No, this must be the camera. Yeah. So first mirror, second mirror, third mirror, and then it focuses in through the lens of the camera, which is represented in this diagram here. At least I'm assuming that's what this is. The first lens, the second lens, and the third lens. Plus, there's a filter here, and then it's showing. I'm assuming how it splits up the light wavelengths. Yeah, very fascinating. A lot of engineering, to say the least, to go into that development of such an amazingly huge telescope. Absolutely crazy huge. So here's the camera information. There's a 3.2 gigapixel digital camera, which will take 30-second exposures. That blew my mind. I mean, some of the best cameras on smartphones these days, they're what, around 100 megapixels. I'm a little behind. I don't keep up with the newest smartphones, but maybe they're pushing 150, maybe even 200 or 250 megapixels. But you need 1,000 megapixel camera to be equivalent to 1 gigapixel. So, yeah, 3,200 megapixels is quite impressive and unbelievable, to be honest. That's a lot, especially for them to start developing this back in the mid 2010s. I mean, that's impressive even by 2025 standards. I mean, we're going back 10 years before that when they started developing this camera. So, for image data processing, it allows for maintenance, bad weather, and other contingencies. The camera is expected to take more than 200,000 pictures per year, which is far more than can be reviewed by humans. Managing and effectively analyzing the enormous output of the telescope is expected to be the most technically difficult part of the project, which is why I bring up a website like Galaxy Zoo, where they reach out to the public and ask them for assistance with all of this information and data that they've collected from different observatories, telescopes, and whatnot. And that way, the public, they could contribute some of their efforts and some of their time, and it's kind of a win-win. You know, you can say that you were part of a project, an astronomy project, an official one at that, when it comes to classifying galaxies and whatnot. I mean, I can say that because I classified hundreds of galaxies on Galaxy Zoo. Not to say that they took my one specific classification as, you know, the final answer. Myself, as well as hundreds or maybe even thousands of other volunteers, looked at the same galaxies and we just gave our opinion. Is this elliptical? Is it a spiral galaxy or whatnot? So anyway, so by 2018, estimates had risen to 250 teraflops and 100 petabytes of storage. So they're talking about, so in 2010, the initial computer requirements were estimated at 100 teraflops of computing power and 50 petabytes of storage, which again, a petabyte is 1,000 terabytes. That is a ton. So the prompt products are alerts issued within 60 seconds of observation about objects that have changed brightness or position relative to archived images of that sky position. So anytime they take a picture, and if there's an object that has moved since the last picture that was taken or any other picture taken before it, if the image notices that there's an object that is either moved slightly or has flickered or has become brighter or has become dimmer, it's going to set off an alarm. And I'm sure the whole thing is going to be automated for the most part. It's not like they're going to be getting, you know, millions of alarms and alerts per day. They technically will, but I'm sure that their software is going to automatically process and catalog all this, and it could probably even, you know, determine which ones are important enough to notify any of the astronomers or any real humans for that matter. Up to 10 million alerts will be generated per night. So that's what this is also talking about. So transferring, processing, and differencing such large images within 60 seconds. See, the previous method took hours on smaller images, is a significant software engineering problem by itself. This stage of processing will be performed at a classified U.S. government facility in California, so events that would reveal secret assets can be identified. These will be temporarily edited out before an unredacted release after 3 days, by which time the data are less sensitive. And that brings me back to, why did the government approve more money than this observatory needed? And they threw extra money at them to try to get this project done, the telescope done faster than on schedule. I believe the reason they did that, which I kind of left a little note to self here, was that it sounds like the telescope has a secondary mission to detect hidden assets, which would be satellites and maybe even weaponry from other countries. So when we're looking up at the sky and they're noticing even the smallest of objects, they said when it took its when they were kind of beta testing the camera and they were running some tests just to take a few sample images from the sky, they in they I guess what would seem by accident, they discovered thousands of near Earth objects, and seven of which were very close or asteroid objects and whatnot. I mean, they just a few pictures and they were already capturing things that they had never seen before. And they're also capturing tiny little objects, meaning satellites and things of that nature. So I'm assuming that the reason why it's going to be run through a classified US government facility, not only so they can filter out the US satellites and government assets and whatnot that it's going to, not by accident, but it's just going to inevitably take a picture of because it's observing the southern hemisphere, and it's supposed to be capturing the entire southern hemisphere over a 10-year period. So there's a lot of US government assets that are going to be in the image. They're going to be in the way. So they want to kind of erase those out of the picture. That way nobody's the wiser. Other countries such as maybe Russia or China, Iran, and other countries that are not too friendly to the US on a regular basis, they're not really going to see or know what's up there, at least based on this observatory. Now, what about those countries? What about China, who launches satellites and who knows what else into space? And the same with Russia and other nations. I mean, I think this observatory could also be looking to capture images of what other countries may have up there in space that we're not 100% aware of. I mean, I think that the US government, I mean, our intelligence agencies, they don't just sit around and do nothing all day. I'm sure that they're very well aware of every launch that happens from every country that's an adversary. Now, we may not know precisely what it is that they're launching, but I'm sure that we can track the launch and we can also track where that object ends up being placed in orbit around Earth. So it's all part of that process where they just have the ability to track damn near everything that happens anywhere around the world, really. But we may not know exactly what it is that they're launching. I have a feeling that this telescope may help provide some insight into that. It might be able to take just a close enough image of that object to perhaps determine more or less what it might be. I mean, it won't allow them to hack into it or anything, but I think that's what this telescope may also be doing, and probably the reason why the government wanted it built as quickly as possible, especially because of China. Their space involvement has been ramping up very quickly over the last 10 years. I believe that they should be finishing their space station. Actually, I think they already did, and I think they recently finished a Chinese space station. I want to say it's in operation right now, though I'm not 100% sure. I don't really follow, space travel as much as I follow astronomy in general. I'm more fascinated with the cosmos as opposed to humans getting up into space and building space stations and stuff. Although it is fascinating too, it's just not my primary cup of tea when it comes to astronomy. So anyway, annual release data products will be made available one time a year by reprocessing the entire science data set to date. These will include calibrated images, measurements of positions, fluxes, and shapes, variability information, a compact description of light curves, a uniform reprocessing of the difference imaging based prompt data products, also a catalog of roughly 6 million solar system objects with their orbits, and a catalog of approximately 37 billion with a B sky objects, which will include 20 billion galaxies and 17 billion stars, each with more than 200 attributes. That is a lot of information. And imagine they're going to be imaging this stuff every single night so they can eventually create a movie. They want to create a time lapse. And they believe that by doing so, it may help them get a better understanding as to how the universe might be expanding or the rate of expansion. And it may help them try to solve the riddle of dark matter and maybe even more importantly, dark energy. Why is the universe expanding at the rate it is? And I mean, is it in fact expanding at the rate that we mathematically believe that it is? And, so on and so forth. So anyway, so the LSST software pipelines are all available as open source software on GitHub. and regular software releases are documented on the LSST Science Pipelines page. So, as far as this new observatory that we're talking about, the Vera C. Rubin Observatory, they did say it's going to take a couple of years before it's going to be publicly accessible in full. But obviously, they're going to be releasing certain images just to keep the public's interest, such as the images that they shared in this article. I mean, we're going to get little nuggets and tidbits of information from the observatory. It doesn't mean they're going to cut us off completely over the next couple of years. Um, so either way, that should be exciting to see some of these first images coming in. So anyway, scientific goals. So yeah, hold on real quick. Let me show this image. This image kind of fascinated me. So these are images of a variety of different telescopes that are either ground-based or up in space. For instance, here's the Hubble Space Telescope down here. Let me see. Is it going to let me zoom in? I guess not that much. Yeah, I'm trying. All right, here we go. Hubble Space Telescope down here, a low Earth orbit from 1990. So that's the mirror. That's the size of the telescope. And to put it at a scale, here's a tennis court and a basketball court, which I felt was a little bit helpful, I guess. James Webb Space Telescope. It's one of the best ones we have, but the mirror is not as big as others. But yeah, but then you get into ones like the extremely large telescope over here, which is enormous. And that's supposed to be done in 2028. So imagine what that thing's going to be able to capture. The unbelievable detail that we're going to be getting from a telescope of that size, larger than an entire basketball court. It's crazy. The same with the 30-meter telescope, which is in the planning stages. I think I read somewhere that they're planning on this being done by 2030, I think. Um, don't quote me on that, but I think I did read that somewhere recently. But yeah, there's the Magellan telescopes, the Very Large Telescope. A lot of these were built in the 90s and 2000s. But yeah, it's very cool. The Keck telescopes, I mean, those are very well known telescopes. I mean, they've captured tons of famous images from the universe. And if I can zoom out here, so this one, you can kind of see the outline here. They canceled this one. It's called the Overwhelmingly Large Telescope, which they looked into, but it wasn't really feasible because the mirror was just simply too large and the cost was going to be too great. Doesn't mean it's never going to happen, but what they were trying to do, this was supposed to be 100-meter wide telescope lens, or a mirror, rather. 100 meters. So yeah, unfathomably. I mean, it's not unfathomably, but it's still an extremely large telescope, which hopefully in my lifetime or over the next, 30, 40 years or so, hopefully they might finally construct a telescope that large. But I mean, we'll just have to wait and see. But yeah, I thought that was very interesting. Crap. Oh, there we go. Good. Glad. Hopefully it'll put me back to where, no, it didn't. All right, whatever. I'll scroll down. Anyway, in the meantime, actually, I'll just show a couple of these images. The L1 lens for the observatory in 2018. So that's one of the camera lenses for the new telescope that just released its first pictures, such as that one. Let's see. So that's an image of the primary mirror, the casting of it. So yeah, that's kind of a large telescope. The mirror is just a little big. Very cool. So we already saw that, or I think we already saw that. No, maybe not. But what is this? Wavefront sensors, guide sensors. Okay, some additional data there. So the life-size model of the Rubin Observatory focal plane array. Interesting. Another image. So this is where we were. We were about here. The top end assembly lowered by a 500-ton capacity crane, which occurred back in March of 2021. All right. So I'm almost done with this. I've read almost everything already at this point. There's just a little bit of extra information I haven't gotten to just yet. So particular scientific goals of the Rubin Observatory include the following: studying dark energy and dark matter by measuring weak gravitational lensing, baryon acoustic oscillations, and photometry of type La supernovae, as well as a function of redshift, all as a function of redshift. Mapping small objects in the solar system, particularly near Earth asteroids and Kuiper Belt objects, the Rubin Observatory is expected to increase the number of cataloged objects by a factor of 10 to 100. It will also help with the search for the hypothesized Planet 9. So they're still taking that seriously. NASA and the scientific community, they're still taking the possibility that Nibiru or Planet X may actually be out there. Maybe. I mean, I know that they've theorized that it might have an extremely high elliptical orbit, which means that it falls into the Earth, into the inner solar system like once every what? Like 3,000 years or 5,000 years or something. And after it falls into the inner solar system, kind of like a comet might do, um, it wraps or orbits, slingshots around the sun, and then it heads way, way out, like way beyond Pluto, far, far, far beyond Pluto, like way out into the Oort cloud or whatever, and at a distance so far away that we just can't see it because it's just simply too far away for its size. I don't know. I guess we'll have to see. That would be unbelievably amazing if they actually announced that they found a planet like that. I mean, it would seem that the conspiracy theorists would be right yet again. So it's also going to detect transient astronomical events, including novae, supernovae, gamma ray bursts, quasar variability, and gravitational lensing, and providing prompt event notifications to facilitate follow up. It's also going to be tasked with mapping the Milky Way. And I believe that was everything that I had. Yeah, there's lots and lots of information on here, comparisons with other sky surveys, the progress of its construction, and plenty of other things. It goes into detail about the mirrors, the building itself. So this is basically what the inside of the building itself appears to be. I don't know where their living quarters would be. Well, maybe they don't even stay there. I figured those who are observing and running this thing, I figured they would have a place that they're going to be, you know, sleeping. I mean, like, where's their sleeping quarters? Maybe that's down here or something. I don't know. I mean, the Atacama Desert, I wouldn't think that there would be a whole bunch of hotels out there. I mean, it's kind of in the middle of absolute nowhere. Anyway, there's an image of the telescope mount assembly of the 8.4-meter Simony Survey Telescope at the Vera C. Rubin Observatory, which at the time this was taken, it was under construction, which explains the boxes and whatnot. Plastic over there, trying to keep it in good shape, nice and clean. Rendering of the Rubin Observatory camera. They cut them off. They're showing a scale of how large it is. There you go. So that's a 5 foot 5 inch tall human, and that would be the camera. Very large, very very large camera. Yeah, that's wild, man. Very very complex, to say the least. Vera C. Rubin Observatory commissioning camera installation. That's what that image is. And this is a 333-second exposure image of the night sky containing 19 or more streaks due to Starlink satellites' light pollution. Oh, lovely. I never even thought of that. That actually really sucks. Image from CTIO's dark energy camera that has a similar field of view to the Rubin Observatory camera. Man, that's going to be a difficult problem to solve. So they're going to be trying to observe the universe through the southern hemisphere using this new telescope, the Rubin Observatory, and they're going to have to deal with thousands of Starlink satellites. They're going to be constantly flying in front of it, causing these white streaks. I mean, I wonder how they're going to, you know, maybe it automatically filters them out. Maybe there's software that they've already developed that allows for them to, I guess, maybe immediately erase the streak as it's happening. I don't know. I mean, hopefully they have, but I never even really considered the fact that Starlink satellites are going to cause streaks whenever images are taken from really any observatory. I mean, pretty much any camera these days, or any telescope these days, when they're capturing an image of space, they usually leave the shutter open for what sometimes can be a really extended period of time. It could be, minutes or even hours. I'm trying to think back how long that the shutter was open on Hubble for the ultra deep field image. I want to say it was for a few days. It was for dozens and dozens of hours that they had to focus on that one spot to capture that insanely detailed image that it captured. So yeah, that's kind of problematic. I mean, hopefully they've got a solution for that, but I never even really considered that fact. So anyway, I think that's probably just about it. I mean, more images of the telescope, the exterior building, And there's an image of the optical engineers Justin Wolf and Simon Cohen with the R filter for the Rubin Observatory camera. That's cool. That's like one of the lenses of the camera. Very large. That looks like the camera. Rubin Observatory camera chilled to sub-zero temperatures using both cooling systems. Wow, man. Yeah, that's about as legit as a digital camera can get. Another image of the observatory. There's another one out there in the middle of nowhere. Maybe that's a city down there, perhaps. Maybe down here, perhaps. But I mean, they tend to install these things very far away from light pollution, which is why they're installed in the Atacama Desert, because there's practically nothing out there. In fact, they in some areas of the Atacama Desert, they receive it's something like less than 1,000th of 1 inch of rain annually. That like there's some areas of the desert where it only they get like um maybe some light sprinkles like once every like 1,000 years or something crazy like that. Anyway, this is like Chile, obviously. I don't know why they didn't put a dot where it is, but all right, that's the Milky Way with the observatory. Another image of the L1 lens. The L1, I'm assuming it's probably the primary lens or the outermost camera lens of that camera. So not a small camera. It's a very, very big camera. It's like opposite of like Honey, I Shrunk the Kids, where they just like blow up the size of a camera to an insane degree. But anyway, that pretty much does it. I don't think that I got anything else. Oh yeah, so how much did the U.S. government contribute to the Vera Rubin Observatory? It looks like the NSF, which is the National Science Foundation, or the U.S. National Science Foundation, and also the U.S. Department of Energy's Office of Science, has contributed approximately $571 million toward the construction of the observatory. And the total construction cost was about $800. So we spent, of course, the lion's share developing this observatory. 75%, give or take, of the total amount of funding was produced by the American taxpayer, which is probably why, in part, that they decided to name it Vera C. Rubin, because she was an American astronomer. But even though it says here that contributions came from about 30 other countries for equipment and also expertise. So I guess they're donating, not donating, but they're contributing their time, not really money. But yeah, anyway, that's about all I got for the Vera C. Rubin Observatory. It's going to be really exciting to see what it comes out with over the next weeks, months. Hopefully they'll keep dropping some new images that it takes, because it sounds like it's going to primarily take the same images day after day, because their primary objective is to observe movement over the next 10 years. So they're going to be taking the same image over and over again in hopes that they'll detect things that either move, or they'll shine brighter, or they'll dim. That's also going to hopefully detect exoplanets that are transitioning across their star, kind of like an eclipse, if you will. So I'm sure it's going to be detecting that too. So we might start hearing about a lot of new exoplanets that we didn't previously discover. That might be hitting the news over the coming weeks and months. I mean, that's going to be exciting too. Always nice to hear of a potential habitable exoplanet that has been discovered. So that's going to be exciting. I'm definitely looking forward to that. So anyway, thanks for watching, and I'll see you later.